Рассказывать я буду по-английски, потому как проще.
I'll be speaking English, but answer questions in Russian.
So let's talk about routing in DC and some history, what happened last 30 years. So starting from the time we started to build data centers in the 90s, we started to do layer 2, spanning tree on top, half of links blocked. In some cases, we did have layer 3 from the leaves up. So everybody is familiar with Cisco's story about aggregation layers, and wasn't very efficient when we started to build out. When more bandwidth became a necessity, more and more need for layer 3 become kind of obvious, because you could route, you could be more efficient, you didn't need to block half of your links. Between 2010 to 15, people started to move to layer 3, starting with Google, Facebook, and everybody who was large enough to develop solutions in home. So Amazon started to run modified version Quagga. They're still on SPF plus BGP plus some other stuff on top. Google started with SPF, moving to FirePass. Facebook is still running BGP in many places with OpenR, which is link state kind of protocol in Underlay. So we see definitely need for layer 3. Every new data center built today is built on layer 3. So routing is de facto standard protocol in data centers. If we look at standardization, so Petya published, Peter published his draft in 2012 that was describing his experience in Microsoft at the time when he wrote kind of simplified version of BGP and how it worked out. It didn't really progress till 2015 when we figure out it's needed. So being chair of routing working group, I took this work, and in 6 months we adopted an RFC, highly successful one, used by many, many people today. So there are hundreds of companies running BGP today in data center. If you look at pretty much anything done by open source community, so Cumulus, FRR, people using BERT, Juniper, Cisco, everybody will tell you today, if you want scalable and manageable data center, run BGP as an underlay protocol. So in 2015, it also became clear that for large data centers, link state protocols are a problem, mostly due to flooding. If you look at when and how link state protocols have been built, we never envisioned this degree of connectivity like in data center when everybody is connected to everybody. So by flooding, we didn't really oversaturate the network. In data center, however, where dense connectivity graph, amount of flooding is overwhelming. It's very possible that every device in the network will receive 8, 16, 24 copies of same advertisement. So it's pretty much killing the network. BGP, being great protocol, has its own drawbacks, which I'll describe in some details. So to look into it, I formed a so-called design team to look into what needs to be done and work on a set of requirements for next generation routing protocol. So first drafts were published, and in 2017, last year, we formed 2 new working groups. One to work on Rift, and this is the protocol I'm going to talk about. Another one is extension to BGP, where BGP itself behaves as a link state protocol. So it replaces best path selection with Dijkstra. I'm not going to cover it here. There are a number of drafts in ATF. If you're interested, you could just look for it. It doesn't respect me. So the reality is not so simple. This is about US 500 companies that could see surprisingly, 45% of them still run EIGRP. Large number runs OSPF and really cries. So they need help. So they actually came to us and asked to help us to develop protocols that would help to solve their issues and have formal document that they could take to their vendors and say, look, this is what we want. So we are working with them as well. There's a group of enterprises in the US at least that works with us on the requirements. So we've built a team of people who know routing, who know data centers, and you know some of them. So Yandex, Piotr, and some other people who are famous and well known for their knowledge about protocols and data centers. So we really like each other, and we've known each other for a long time, but this is not why we built the team. We built the team to work on requirements for a protocol. Maybe in 20 years from now. Actually, it looks a lot like Randy. So we know how to build stuff, and the intention was to write spec that would represent both coding community as well as engineering community, people who operate data centers. We wanted to avoid beauty context. You know, the discussion about BGP versus SPF versus SS have been going on forever, right? So specifically to avoid this kind of stuff, right? To have common set of requirements against which new protocol could be compared and have decision process which would lead us to kind of the best in breed protocol. So the draft was published to bootstrap common work. However, we are open to comments. We are open to, we need your help because you are the people who really run this stuff. You know, whatever we do in ATF, if it's not connected to reality, it's worthless. So what's going on? As of today, we've got 3 types of routing protocols. Distance vector ones, so Bellman-Ford. You tell your neighbor what you know about the network. We run link state protocols, most popular being ISS and SPF. And we tell of the network to our neighbors, right? So everybody in same area level knows exactly how network looks like. The major property of link state protocol is that LSDB on every router is exactly the same. And path vector, which is BGP, which is modification of distance vector. In this case, we advertise our neighbor about nodes or IS paths within our own network. So why link state protocols and why not? The advantages, we advertise everything. We can build full topology graph with all the attributes. And not only connectivity, we could provide a lot of data about attributes of the link being load, jitter, quality, whatever not. So it's easy to do traffic engineering. It's easy to apply some business logic on the network graph. However, disadvantages are anytime something changes, you have to rerun SPF on every node in whole network. And believe me, you don't want to run incremental SPF. That's why Cisco deprecated it and others never implemented it. Flooding in densely masked topologies such as data center is problematic. And it's probably not if you've got 40 switches. If you've got 200 switches, it becomes a real problem. And reflooding contributes to this problem because no one is flooded at the same time, so you've got constant flood of packets with updates. Distance vector pass protocol, so distributed Bellman-Ford. As you pass, you add metric to your link. So when implemented in the way BGP does, scales extremely well. When implemented such as RIP, you hit well-known problem, which is count to infinity. So you are dead after 15 hops. The problem, however, is slow convergence because every node, when it receives update, it has to process it and then advertise. And we see this mostly in BGP. BGP in large fabric converges slow because you are not allowed to re-advertise update before you process it. So you receive an update, you run best pass, Depending on implementation, you'll go and verify whether it's in RIB and FIP, and back then, you'll go and advertise. It takes time. So this graph shows you the difference. In link state, you reflood immediately on update and then process. In distance vector, you receive, you process, you re-advertise. So in order for your update to reach everybody, it takes time. That's why internet pretty much never converges. It's an eventually consistent database that eventually converges, but de facto never, right? So both problems manifest itself in either slow convergence or excessive flooding. So when designing the protocols, we mostly try to apply them to FAT3 topologies because it's a 99% of data center. Obviously, when you start looking into more advanced use cases, distributed state, machine learning, there are some other things, but again, we are trying to be pragmatic. And while there is still 1% of problem that needs to be addressed, we believe that for 99% we could address it with the new protocols. So RIFT stands for routing in FAT3s. So FAT3 is the topology, routing is technology we are using. I'm going to talk about concept and some of very important properties of RIFT. So I'm not going to try to explain you in details what protocol exactly does. However, hopefully there's enough information to interest you so you could go read the draft. And maybe next ENOG we could go in detail how stuff exactly works. So for quite some time we've tried to adapt BGP. So all the hacks with accepting ONIS paths with add paths added a lot of complexity and whatnot. We've tried to hack around ISIS or SPF. Again, a lot of complexity, and eventually figure out it's easier, maybe not easier, but better to start from scratch, to design new protocol rather than trying to adapt old one. So I'll go with you through a set of requirements that were published in the DC routing requirements draft and how RIFT is trying to address them. So first requirement was zero-touch provisioning. RIFT gives you ability to have single level configured, and then the rest of the fabric will completely go and figure out where they are, who they are. Peer discovery and miscabling. RIFT gives you ability based on where the node is to understand whether it's in the right place in the right hierarchy, whether cables are connected to the right ports. Minimum amount of information. So the key property of RIFT is that it is link state protocol when it goes up towards the spine. However, it's distance vector when it goes down. Meaning when you go down, you only advertise default. In some other cases, you would advertise some additional prefixes. However, amount of state is minimal. And if you use cheap silicon, old version of Broadcom, it's very important to keep number of prefixes low because your LPM table is the most is the most expensive resource in the switch. So again, since you're only advertising default route down, most likely you'll end up with 2 routes on the leaf. ECMP is important. Ability to do weighted ECMP is even more important. We all know the problem with elephant and mice flows. So provide facility to compute a metric that represents your bandwidth and not just metric cost is important. See all the links, spine and any device that could be connected to a spine sees all the topology because it's link state up, so full SDB is known. A few more interesting attributes. So today, if you want to provide some opaque data on top of your basic reachability, you need to, in OSPF case, provide new type of LSAs, and takes years. In case of ISS, new type of TLVs, and again, takes years. RIFT gives you native facility to configure what we call policy and key value prefixes that could be used to transfer this information up and down. So if you need to provide, I don't know, geographic location or temperature, it's not just there. You can just use to encode information. If you read the RFC 7938, which is BGP in large GC, it specifically talks about not to aggregate prefixes due to black holing. It's a kind of larger discussion why. However, if you aggregate your routes and then next hop fails, you'll black hole. Rift provides a unique ability to deaggregate on demand. So in normal working condition, you would always send default route. However, if there is loss of connectivity up or up, you'll figure out, and I'll show you how, and you'll start sending more specific prefix. And last thing, probably most important one, Rift is schema-based protocol. It's based on drift encoding. So practically, you could add your own pieces to protocol, recompile the schema, and have new protocol in 15 minutes. Compared to changes to OSS or SPF, which potentially could take years, it gives you ability to innovate in your own way. So you run your own data center, you figure out you need some additional piece of information. It will take you 15 minutes to encode it, to recompile the code and start running. So it's the first protocol. It's the second protocol after OpenR, only used by Facebook today to provide schema-based encoding. So I've put significant amount of information to explain terminology. It's more for you to read after the presentation, to read the draft and really understand easier what it means, right? So some basic information, how we see data center. So it's level 0 for leaves, and then levels 1, 2, and higher for spines. We define directions. North direction is direction up towards spine. South direction is direction down towards the leaves and servers. Again, it's for your home reading, really to understand the elements used to establish relationships, to exchange information. They're pretty much the same as in ISS and SPF. We didn't reinvent the wheel here. We reused what's there. It's well known. It's working. So, as we said, we always have a topology sort. So we start from level 0, that is the leaf. In definition of Rift, it's a node that doesn't have any switches below. Prefixes usually propagated from level 0 up because servers are connected to the leaves, right? So how does it work? When we flood information from a server to the leaf throughout to spine, when we go up, we always send all the information. So it's linked state up, as we said, right? However, when I need to propagate information down, if I'm on another leaf in another pod, the only information I need to know is how to reach a switch that is higher in the level. In this case, I only need default route. So when I send information down, it's a distance vector, it's default only. Sorry, very interesting property is that we bounce up. What does it mean? When a leaf advertises something to a spine, spine will re-advertise same information down. When we advertise something from a leaf up, every spine will have information about itself, because when we re-advertise it back, we will also re-advertise information received from another spine. Why is it important? In classical leaf and spine topology, devices at the same level are never connected. So practically you have no way to exchange reachability. Since we bounce it up, you know exactly how your neighbors at the same level are connected. And this gives us ability to deaggregate. So we'll go through this case. At this point in time, you should know that every device at the same level has full view of connectivity of every device in the same level. So automatic disaggregation, against unique feature to Rift. No other protocol can do it. So when a link on the up red switch breaks, this information is going to be advertised down to every spine, right? When this information reflected back, another device at the same level would know that its neighbor lost connectivity. In this case, it knows which prefixes are reachable through the interface that has failed, and it will go and deaggregate them. So not only default route is going to be sent down, but also this aggregated route itself. So in this case, when you are going to start sending traffic, you'll do lookup. If it matches your default, you'll do it as before. However, if it's specifically prefix that was reachable through failing device, you will send it over device that still has the connectivity. So this is a unique feature and gives you ability to do aggregation on the working fabric, and when something fails, it will deaggregate on demand. So this is pretty much the most important features you should know about. Same understanding gives you ability to do, if not faster, it's very fast, it's in milliseconds, but pretty much link and not protection. Because we know the topology and connectivity on upper layer, we could always reroute traffic through another node when we see the failure. And in initial implementation, that's, okay, it's a beta gamma code, we see recovery times in order of 3 to 5 milliseconds, so it's extremely fast. So, besides the points we've described, RIF does automatic flood reduction, so it will go and partition pods into flood domains. So you don't flood anymore across all the fabric. Your flooding domains are very small. Leaf-to-leaf shortcuts. So imagine you are doing something like machine learning and sending data up is not working. You need to be really fast and contained within your data set. With Rift, you could provide routing over this kind of links without looping. So we talked about model-based packet format. We are not bound to any transport. Today's implementation is over UDP. However, nothing prevents you of using QUIC or any other protocol, transfer protocol on top of your choice. There's no purging. And remember, we give now native support to support any kind of opaque data moving up and down. So if you want to encode something that is not reachability, but still important for you, there's packet type that gives you native facility to do so. So status in industry, obviously there is working group in ATF. The initial individual contributor draft, the draft Shende, has just become adopted as a working group document, so it's officially document ATF is working on. There's implementation by Juniper. Potentially they're going to be open source implementation. You could download working code from Juniper and play with it on your laptop. It's available, link is not here, I can provide it. We are working on extensions to beer. We are working on extensions for segment routing. There's already young data model to manage it. So a lot of work and good progress. И вопросы?
Please, any questions? Что, правда, нет вопросов?
Hello, Gennady Abramov.
Gennady Abramov from CityLink Telecom.
Directly to the presentation, let's say some kind of common question. Do you have any suggested readings such as O'Reilly, etc., to have a better overview of modern DC routing technologies? Because for me, at the moment, there are many sources that you must put together. Do you know any, let's say, suggested reading to for that?
Good question.
Surprisingly, most books today are focused on overlays, so EVPN and such. And there's a pretty good book by Cisco called EVPN Nexus View Really good book, actually. I did technical review for it. I like the book. So if you think about underlay, and Rift is really for underlay,
yes,
it assumed it's just working, right? So I would really advise on reading the Peter's RFC 7938. It describes exactly how BGP works, what the problem we see in underlay, and how to work with it. We've done a number of podcasts on Rift, one with Ivan Pepelnyak. I assume everybody knows who Ivan is. Another one with packet pushers, and third one with Network Collective. So there's 3 hours reading and a lot of questions and answers. Actually, they're pretty good. So it's a good place to start. In general, I really like Ivan's, so the IP space by Ivan Pepelnyak. He has a number of webinars, has a number of very good documents about how data centers work, difference in technologies. He's also covering some vendors and how they interwork. And so I would start there.
Thank you.
Alexander Gorbo, Syrian.
Alexander Syrian. So when the standard is launched, will it be restrictive? Will there be some restrictions about the current algorithm and protocol and simultaneous implementation of Rift? Actually, no. Rift by itself is underlay protocol. It gives you reachability if your overlay uses VXLAN, EDVN, or any other technology that's used as overlay today. Overlay is next hub. Rift will give you next hub, and what it gives you is loop-free topology in the same way as OSPF or LS and SLS, and there are no restrictions in this case. Underlay completely disconnected from overlay. More questions? So, hello, Alexei Bogomolov. I have a question. I'd like to know more about Rift positioning in the protocols, routing protocols family. So first, is it something exclusive EGP protocol or some potential to go further? From the positioning point of view, on one hand, if the data center is large, so 100+ devices where the flooding becomes a problem, then Rift will address it. On the other hand, if the data center is less, but you are interested in the touch provisioning, so the just to add up a device, and it should configure and understand if the cables are correct, then that's where it can be also used, considering that the Rift has embedded transport mechanism, additional mechanisms, so you can use in BCI, where with the metrics you need to have delay and length, fiber optics, and some additional properties of link that cannot be transferred by a normal routing method. So correct me if I'm wrong, if Rift, roughly speaking, starts from the server, it is possible. Implementation of the server will be much simpler than implementation on spine, because server gets default route and does not any route computation at all.
Yes, the implementation can be written into weeks, and then so then the next question: so to what extent will be correct to use not underlay protocol, but to use it as overlay protocol of a higher level, of a high order? So meaning that to control the mobility of virtual machines, distributed. So for overlay, we use BGP. For a reason, BGP cannot control the mobility of machines. VPN does it very well, using the mobility community. VPN, right, but there are problems there. So it's not standardized. The mechanism has not been standardized except GARP and other protocols, which provide information that the virtual machine just moved from one data center to another data center. So then sometimes they should say to everyone that's what happened, but you need. So then such complex connections, they're not used, and especially such complicated data centers and operators not used. From the viewpoint of the distribution of information, the RIFT does not give you a chance to do HD constraints and other mechanisms that exist in multi-protocol BGP. And so in theory, yes, you can use overlay protocol, but in practice, presently BGP is much better. It's a better protocol. BGP is much better because it was built for VPNs. So because we have one last question. Okay, one last question there. I have two questions. First question, correct me if I'm wrong, that a RIFT can be used only for cluster. A RIFT can be used. The technology is based on monotonous increase of metrics when it goes down, when it goes south. It's only if you build a horizontal link between lifts that is not CLOS, and that's supported. That is supported. On the other hand, if your topology is not CLOS or CLOS with some additional things, then RIFT is not the best protocol for you. Meaning that there is a list of requirements to topology that need to be observed, right? Yes, in theory, yes, you can do RIFT. RIFT can operate as a BGP, one update per packet, and then it will work anywhere. But then its efficiency and meaning disappear. So you can use it if you are interested in this. If you want to develop your own additions to the protocol through skin additions. So, for example, replace ISS for RIF somewhere in Champagne. And the second question: you have plans to teach a RIFT to assign, distribute marks to teach. RIFs to distribute SLNP. Yes. We're working on these routing extensions, and SPSF-SS. It will have an additional field, so which in its turn will have a label value. So then it will distribute labels. And then RIFT it will distribute labels, and it's extendable. So then you could take the design how labels value transports through a RIFT using Viport. It's transported, and so I'm going to publish a draft that will tell us how the labels can be transported. Thank you, Jeff.